Testing. Okay. Awesome. Thank you guys so much for having me. It's a little daunting to talk to all you guys. I flew in for Texas a couple days ago, so I'm a little out of it. So give me a couple slides to get going. Bear with me. But my name's Tyler. I work for Cisco Talos, and this is my talk in the zone OS X heap exploitation. A small disclaimer. We're going to talk about heap exploitation. This has a Safari exploit at the end of it. But a lot of this is heap reversing. And every time I was reversing, it's reversing with the goal of exploitation. But this talk has a lot of low-level heap stuff. It's very similar to like a Chris Valasek talk on like low fragmentation heap, if you guys have ever seen one of those. It's very in-depth, very technical. If you could hold your questions off, I have a couple points in here when you guys can ask questions. I'm trying to keep it as simple as I can, so bear with me. Okay. Here's the obligatory Cisco Talos slide. I'm a vulnerability researcher with Cisco Talos, meaning we try to find bugs in open source, closed source software. We do a lot of reverse engineering, bug finding, fuzzing, all that kind of good stuff. Well, I'm the one up here giving the talk. I'd like to give a huge shout out to every guy up there on the list, because every person there has helped me get here, helped me do this research, and helped me along the way. All right, I don't know if you guys saw this, but a month ago, give or take, I released a couple bugs in iPhone. And a couple of reporters picked up on it, and they started saying, oh, this is the next stage fright for iOS, this is that. Well, nobody really quite understood what these bugs were, how these vulnerabilities would be exploited, how you could actually attack these via something like iMessage. Is any of that actually possible? Well, I'm going to tell you all that here, but the media kind of went crazy with it and went a little overboard. So I don't know if you guys saw that, but that's what this talk is about. Here's the two bugs that are used in conjunction to get remote code execution. And you can check them out, like I said, on Talos blog. There's all the details on this, proof of concepts. There's a full reverse report of why this bug is triggered, how this bug is triggered, how you'd fix this bug, how all these things are fully reported on Talos' blog. So I think it's blog.talosintel.com. Check it out, and I wrote entire write-ups on all these. All right, so why did I do this research? So like everybody these days, I was fuzzing some images. The cool thing about images on OS X is they also hit iOS. So I'm fuzzing some images. I find a bug in a TIFF-based heap overflow, pretty common heap overflow, and so that's going to hit me Safari. That's going to get me almost every product on iOS. That's going to get me Preview. That's going to get me a lot of stuff. So I'm saying this is just a good bug. Let me move forward and try to exploit this bug and get a full remote code execution bug out of this. There's not a whole lot of documentation on OS X. Dino Daizovi is probably the most famous researcher that's done this, and his last research came out like 2009, so that's roughly 7 years ago. So we get here, I get this bug. What do I do first? I throw out a huge JIT spray. I throw this massive JIT spray. I have code execution in Safari in less than a day. Well, I'm getting code execution 1 out of 100 times. This is not something I'm proud of, so I wanted to reverse this heap a bit more and try to understand how can I get code execution 1 out of 10 times, 1 out of 5 times, get a nice, reliable, full exploit out of this. And as you guys are going to see, it turns out that it's a lot more difficult than I imagined. So I'm hoping most of you guys have at least a general understanding of how the heap works, the general ideas about heaps. This is just a bunch of talks about heaps. Chris Valasek's an idol of mine, and I love all his talks, so I highly recommend it. Here's the prior work on OS X. 2005, there's a bunch of articles in Frac. 2009, Dino released a book. And 2010, Matt Gallagher actually released a blog post. It's maybe 200 words long, but it's actually probably the most in-depth look at the OS X heap to date, besides this. So we did all the research on El Capitan, 10.1.5. It works on 10.1.6, and I checked the Sierra beta over the past couple days. The Sierra beta is identical. So the next version of OS X has no changes to heap, so all the tooling and research we've done will still work. So here's a slight roadmap of what we're going to do. We're going to do some heap structures. Hopefully you guys don't fall asleep during the heap structures. I know they're boring. If you could just bear with me, I greatly appreciate it. Then we're going to get into some heap strategies. We're going to talk about stuff like metadata overwrites. We're going to talk about heap coalescing. We're going to talk about the cache. We're going to talk about those sorts of things and how we can use some of those to take our heap overflow and make it into a different style of bug and make it into something that we can actually exploit. And then we'll talk about exploit strategies and how we went about fully exploiting this and how much of a pain it was. Okay. So here's just a list of common heap implementations over the past few years. I break them up into 2 categories. We have category 1, which is linked list style allocators. Linked list style allocators simply just walk through a linked list looking for blocks. They're not really sorted by any size. They're just kind of put together with forward links and backward links. This is like the most famous implementation. This is probably Doug Lee malloc, and that's where the original 4-byte overwrite, heap overflow, header overwrite came from. So that's this general idea. Well, in 2016, we have something called arena-based allocators. Arena-based allocators base things on size. So as you can see here, these are all just buckets, and there's arbitrary number of buckets, and each bucket is based off a size. The most common implementation of this is like the low fragmentation heap. So everything is going to be bucketed on similar sizes. We'll get into how OS X uses this and what that means as we go. All right, so I have to talk about a quick little bit about OS X just to get you guys thinking. So OS X Core Foundation is like libc for C. So anybody that's programming C is usually libc for everything. If you're programming in Objective-C, Core Foundation is your gold mine. It is going to do pretty much all graphics connections, all cross-site communications, all communications in the kernel. Core Foundation is very important. And why this is important for us is WebKit, as we know, is in Safari for that instance, and for that matter, is a multi-platform thing. So WebKit has to have its own malloc implementations, has to have its own free implementations, has to have all that stuff built into it because it has to work on Windows, Linux, and OS X. But at the core foundation still has to be used to render the images and things. So that's going to come into play later on. Just keep that in the back of your mind. Okay, so I'm going to just talk a small amount about some of the utilities that come with OS X, just because it's not the most popular platform. You have things like guard malloc, which is very similar to Heap, but Heap is actually taken from OpenBSD's original allocator. And because OS X is based off of BSD, they basically just took their allocator with them. So that's guard malloc. It's super useful if you're fuzzing and you're not using guard malloc, you're doing it wrong. Okay, so malloc stack logging, another awesome thing. Malloc stack logging is actually going to give you all the information about allocation. When it was allocated, when it was freed, all that kind of good information right by default. There's no other allocator that gives you this information by default, so that's super useful. So you have two ways to do it. LDB wrote a thing called malloc info, and malloc info will segfault your computer 9 times out of 10. So I don't use that. What you use is malloc history. And what malloc history does, as you can see this little picture, is you go to the terminal and you type in malloc history, and you type in the PID and the address, and it gives you back a huge stack log. I wrote a couple tools to make this a lot easier, and we'll talk about that more as we go. All right, the OS X heap. All right, so we have, I like to think of this as like a large umbrella. And if you had one big umbrella and you had 5 of your best friends, what would you do? You'd all try to stand on that umbrella and you try not to get wet, right? If there's a hurricane happening, you're all going to try to stay on that umbrella and not get wet. That's kind of what this overarching zone structure is. We have an overarching umbrella, and inside the umbrella there's slots for each individual malloc. So we have the scalable malloc, scalable allocator, the magazine allocator. All these allocators have to live together inside one program, and that's what this overarching zone structure does for us. All right, so the magazine allocator is used by anything that uses the default system malloc. So everything like color sync, Safari, Keynote, all that kind of good stuff is going to use the default allocator. What doesn't use the default allocator is WebKit. So that's a huge problem. And then when you render images, ImageIO also uses its own internal malloc, but it mostly uses the default system malloc. Okay, so the free list we talked about a little bit. It's just a bucket free list, an arena-based free list. There is cookies and checksums to prevent heap overflows, and we'll talk about how to get around those in a few minutes. So every region or arena, the place where you actually get the allocations from, is going to be bound to a core. So you're going to have 1 magazine per core. This particular laptop has 8 cores. 4 cores, 8 magazines because of hyper-threading. And then you have 1 special magazine for the depot. And the allocations are going to be divided into 3 sizes, tiny, small, and large. So what that means is each tiny is going to have 8 magazines, small is going to have 8 magazines, and large is going to have 8 magazines. Tiny and small allocations are managed by a size called quantum. From now on, anything I say as far as size, I'm going to say size 1. When I say size 1, I mean size 16. You can just take whatever number I say and multiply it by 16, because that's what the size of what the quantum of a tiny allocation is 16. And so I'm probably going to go, we're going to talk mostly about tiny allocations. We're not going to talk too much about small allocations. And large allocations, while potentially useful for exploitation, are not going to be discussed in this talk because they're irrelevant for what I was doing. So the memory itself comes from region, bucket of free list, chunks get moved to free list, the entire free list is coalesced, and then when a region's empty, it gets moved to depot. Okay, so the interesting stuff on this slide is just the way the metadata is set up. It just has metadata to tell you whether a block is free, whether a block's in use, and how big those blocks are. And that's the tiny metadata uses two separate bitmaps to do this, and the small metadata is actually able to do this with just one singular bitmap, which is a little easier. And this large allocation stuff, again, you guys can talk about yourself. You guys can read over later, and I have more information on it in the slides. Okay, so thread migration. I'm assuming most people understand the idea of thread migration. Essentially, when your kernel blocks to, when your user land blocks the kernel, that kernel is not required to wake up on the same core that it went to sleep on. So that's great. But if you remember correctly, I told you that every magazine is bound to a core. So that means if I set up magazine 1, I set up, I heap spray it, I massage it, it's perfect, exactly how I want it. And then for whatever reason, I do a file input, output, something like that. I do a network call. It blocks the kernel for a second, comes back, and now it's on core 2. Well, all the work I did on core 1 is now gone. It's still there on core 1, but but when I malloc, it's kind of come from core 2. So as you can probably tell, this is going to be a huge problem when you're trying to exploit something. I'm trying to massage the heap, set the heap up perfectly, but then I also have to make sure the kernel never blocks, because if the kernel blocks, I'm going to get woken up on a different core, and it's not going to work. So the core determines the magazine, and the magazine determines the heap layout. It's almost impossible with migrating cores to set up your heap properly for exploitation. Apple actually has a patent on all this information. It's like a 4,000-page document. I don't know how to read patents, so I didn't put any information here, but you can Google it yourself. And they essentially patented their thread migration techniques. So while I believe it's mostly a performance-based thing, it actually works extremely well as a heap overflow-based defense, like a defense against heap attacks. It's just pretty interesting. All right, so how do we do that? How do we fix this? How do you fix the core blocking issue? Well, the way you do it, or the way we were able to do it, is you set up different JavaScript things to block. You just try to block as much as you can. You try to get as many tight loops, as many things going as you can, as many threads running as possible, and that's able to get you twice, 3 times, 4 times as many iterations before the kernel is actually going to switch cores, and which actually is going to open up our window just big enough that we can get our exploit to work. Okay, I'm going to burn through these pretty quick, just so we have some more time for the demos and stuff. This is mostly just structures, and they're important to know, but they're not the most important thing in the world. All right. Okay, so this little interesting part is that each magazine contains a cache. And what a cache is when a allocation is freed, it goes directly to the cache. And so that way when another allocation comes that wants that exact size, it can grab from the cache very quickly. What's the point of this? The point of this is that Objective-C makes a million small allocations, 8-byte allocations, 12-byte allocations, 16-byte allocations. It makes them very frequently, very often. So this cache actually works extremely well. What's different about this cache from other caches is that to get from the cache, you have to allocate that exact amount. So if in the cache there's 32 bytes, and you allocate 16, it's going to come from the free list, not from the cache. It has to be exact. Okay, zones. The major feature of zones is extensibility. We can have multiple different malloc implementations inside of one overarching structure, and that's what these zones do for us. So zones are just going to be a zone name and a version. The versions are going to be how you determine what malloc implementations is. So WebKit uses version 4. The default system malloc is version 8, and those versions determine how we're going to call malloc and calloc and all those good things. Okay. I just want to do a quick 2-second digression on the FRAC article, just in case anybody's seen it. But everything that Nemo said in his FRAC article from 2005 is obsolete, as you can expect. It's 11 years old. His research was great, and all of that was wonderful, and I used it a lot to help guide me into my research. But it's all out of date. It's all super old, and that's why we went ahead and did this so much research, just because it had never been really talked about before. Okay, so this is the S zone T sitting inside of a zone. An interesting thing here is the cookie itself. So what a cookie is going to do, skip ahead, what the cookie does is you take all pointers that are going to be on the free list and you XOR them with the cookie. You then run it through a checksum function, and that gives you a checksum that you put as the top byte of your free list pointer is now a checksum cookie. So what that means is if I overflow into the metadata of a freed block, I'm going to overwrite this cookie. And if I overwrite that cookie, it's going to check the cookie, and then it's going to bail out on us. Well, what's fun about all this is they actually never use this. All this code is there in place, and no default system allocation, no default system application uses any of this checksum code, any of this. But I would expect to see this soon, because this was added pretty recently, and it's a really good heap overflow detection mechanism that's just not currently there. Okay, so tiny zones. Interesting thing here is the number of small slots. So by default, there's 256 small slots, but it's hard-coded into tiny to be only 64. So they only use 64 spots out of a 256-byte array for whatever reason. And then this is very similar to small, almost the same thing. And notice they have the number of small magazines, the small magazines themselves. Tiny also has the number of tiny magazines and the tiny magazines themselves. So that's how you can actually access those things. And we have large just for completeness. Okay, and then so 1 magazine per core, like I said, plus there's 1 for the depot. What the depot is a depot is a cache for regions. If a region gets full, what do we have to do? We have to get another region, right? Because we still need more memory. So, but if a region gets empty, what happens? It goes to the depot. So when you need a new region, you first look at the depot and try to find the region you need in the depot. If that doesn't work for you, then we allocate another region the old-fashioned way. All right. And so here's just a couple pieces of data on it. The mag free list and the mag bitmap are to show you to quickly and easily query what's free, what's not free, and to quickly and easily see that kind of information. The mag bytes free at end and free at start, that's the information so we can know where in our region are we. Well, I know the region's a slightly confusing term at this point. We'll talk about that more, but that's to determine, do we need to get more bytes, do we need less bytes? Here's a little picture. You can see that's basically what it means, mag byte free at end, mag byte free at start, and that's the stuff that's in use. So as you can think, if you were an allocation scheme and you needed more memory, you probably would just go look at the end and say, hey, look, I have all that available memory, let me get some more memory. That's more or less how that works. Okay, and then this is the little cache algorithm, which is pretty interesting. You have to store like the size of the cached allocation along with the address. So they actually just store it. They have a little technique here using the lower 4 bits to represent the quantum size, and so that way, with one address, you can have the address and you have the size all in one thing instead of having to have multiple entries. Okay, and here's the free bitmap. It's just like any other bitmap. It's pretty straightforward. If there's a 1, that means that there is something in that free list. So that means what it'll quickly do is it'll quickly check the bitmap and say, hey, is there 1 there? If there is a 1 there, it actually goes through physically the free list and walks through the free list, getting the next items. Okay, and then notice these free list pointers are checksums. You remember the checksum we talked about up there? And these pointers are checksums, and like I said, it's not in use, but that's their the idea there. Okay, this is what a free chunk looks like. Previous pointer, next pointer, and forward size and backward size. What I want you guys to do, if you can, is just think, if I gave you an arbitrary overflow, and you controlled forward size and backward size, what you would do. Think about how that could potentially be used to turn it into attack. We'll cover exactly what I'm talking about later. It's just useful if you kind of think about it a little bit. All right, so here's here's a list. There's a look at the bitmap for a tiny region, and notice it's full, but it's only full for 64 slots. That's a hard-coded number, and as far as I can tell, I'm not 100% sure why it's hard-coded to that. I think it has something to do with the fact that this malloc implementation is also used on the iPhone, and for whatever reason, this is a performance enhancement on the iPhone. This is a small region, so notice it's 256 slots, and it uses all 256 slots. Okay, and then so we have magazines. So we have zones. Zones have magazines, and then inside a magazine, there's regions. Regions are where the actual memory comes from. These are typically called arenas on most other malloc implementations. There's 2 different kinds of regions: a tiny region, small region. So they're broken up to quantums, 16 and 512. We have all that metadata containing information. Pretty straightforward. We'll skip ahead of that. All right, so here's what a tiny region metadata looks like. So notice there's a block for headers, and there's an in-use block. So if you want to find the header block, if you want to find out how big a block is, you just go to the header block. You notice the first one is 3 quantum because it has a 1 and then 2 zeros. That's meaning, okay, that's three spots. Now if you want to see if that block's in use, you have to check down the in-use header as well and see header, in-use, both are 1. Now if you go forward a bit, you can see a red 1 and 0. That means that block's actually free. If both of them are 1, that means it's in use. The red one means it's free. That's how tiny metadata is done. How small metadata is done is slightly different. They actually take the high bit. The high bit is actually set if the block is free. If it's not free, then it's not set. And and the number at the back here represents how many blocks it is. So this particular one is 1 block, then we have a 2 quantum allocation, then we have a 1 quantum free allocation and 2 quantum free allocation. We wrote, I guess I forgot to mention this, but we wrote a tool to query all this information. We wrote a tool that does all this for us. I think, I'll skip forward. We wrote a tool that does all this. We call it Heap, and it does all this malloc introspection. It's the only OS introspection tool available. And what it allows us to do is we can actually look at all this information. We can actually peek in and view these bitmaps, and we've written nice helper functions that are very easy to show you, hey, what's free, what's not free, how does this metadata look, in human readable format. This is great for computers, but it's kind of hard for a human to see. Okay, and then large region stuff. All right, and so then the region trailer itself is how you actually access the region's memory. So we have previous and next pointers to actually walk this linked list of the region, And then what index we're on. So what core are we, magazine who retains ownership, so what core are we currently located on? Because remember, we cannot switch cores because, we cannot switch magazine indexes because magazines are bound to cores. If you do that, that's going to muck everything up and not be a good time. All right, is there any questions on any of that? I know it's probably confusing, but we're going to go into demos and stuff, and hopefully it clears itself up. All right, the other thing, yeah, so I wrote Heap. This has all been, I released Heap a month ago, give or take. It's all on GitHub. I highly recommend checking it out. I'll show you a lot of what it can do here in a second. It's pretty cool. All right, so cache. So to empty the cache, talked about this already, you have to malloc exactly the same size as what's in the cache. So if the cache is a 32 byte block, you have to malloc exactly a 32 byte block. Why is this important? Because you cannot really massage the heap with a bunch of stuff in the cache. If you're freeing things and allocating things, you have to know exactly where they're coming from. And I can't be having potential allocation come off the cache. That's going to mess up my exploitation. All right, so we talked about free lists. It's just a index by quantum size. It's bucketed linked lists. Tiny 64. All right, so small. The minimum size is 1009 for a small slot. What's interesting about that is that a small quantum is 512. So that means the first bucket on the small list is 512. Well, if the smallest allocation you can make is 1009, that means any allocation that falls in the 512 region is dead. So if you have a 1009 byte block and you take only a little bit from it, and now it's a 512 byte block, it's dead to you. So what you can find in Safari and things is you actually get a lot of built-up memory stuck in this small region for whatever reason. I don't know why they chose to make the small bucket that size, but it leads to a lot of dead memory. All right, coalescing. So I don't know how many people have exploited heap overflow in 2015, even 2014, but they're hard. They're not easy. They have a lot of checks. They have a lot of heap massaging, a lot of things are needed. What's an easier bug class to exploit? A use after free. If I have a use after free type bug, that's been documented and documented and documented over and over and over, and it's pretty standard how you go about attacking that. So our original goal was, how can I take this heap overflow I have in image.io into a use after free in WebKit? That's our goal. And it's not entirely possible, but we made a valiant effort at it. So how we do that is with this coalescing idea. And I'm going to do my best. I'm going to spend 5 minutes on this slide, do my best to explain this. And please throw as many questions as you got if you don't understand. Okay, so imagine you control the blue block, the blue 2 ones right there in the middle. You can arbitrarily overwrite as much as you want. So what you do is you arbitrarily overwrite into the red block. And remember, we saw that what the free chunk looks like. And I told you guys to think about what would you do if you had an arbitrary overflow into a free chunk. Well, what you can do is you can actually overwrite that backward size. You overwrite that backward size right there, and you point it back into another freed block. So if I take if I overwrite the backward size and point it to that orange 0 all the way back there, when I go to coalesce these blocks, it's going to now say, okay, hey, my backwards queue points to a free block. If your backwards queue points to a free block, that means everything between you and that block is free. So what you can do is by pointing it back there, you then take all those ones that we already have, and now they are considered free by the allocator. So what will happen is when you go to allocate another block, you can potentially have 2 blocks allocated on top of each other. If you have 2 blocks allocated on top of each other, that's almost identical to how a use after free would work. So by allocating 2 blocks on top of each other, I've now turned a heap overflow into use after free, and now have a much higher chance, a much better chance of being able to actually land this exploit. Does that make sense, or do you want me to talk about it again, or is it relatively clear? Okay. So the same idea is possible with forward coalesce. It's the same idea. Imagine you control that green block. You're the green block. You overwrite into the red block. You overwrite its forward size to point forward, and that's going to coalesce all those blocks together. And now you have, again, multiple free blocks that you can allocate from that shouldn't be able to. You shouldn't be able to allocate blocks from there. All right, and then your standard you still have your standard linked overwrites, but like we said, it's not super useful because of ASLR. Obviously, we don't have anywhere to write. Also, because of checksums and things, it's 7% chance. Do you know that Adobe has a technique to overwrite the checksums accurately, but they actually check for that nowadays, obviously, because it's in a book. So that's all updated as well. So that's not possible anymore either. Okay, so here's what the free list looks like. And generally how it works is, let's say I wanted a 3 quantum allocation. What I would do is I'd go to block 3, and I'd see that's empty. So that means I'd move forward to block 4. I'd walk down to the end of block 4 to the 180 block, and I would take that block, and that's the block I'd get. And notice that bitmap over there represents generally what that free list looks like. You can see the one quantum free list, the one quantum, 2 quantum, 4 quantum, all that stuff is represented by the bitmap, which I'll show you in a little bit. And that's more or less how I allocate in the free list. So let's talk about this one more time. So if we want to allocate something, predicting where an allocation is going to come from is extremely important for exploitation. If I can tell you exactly where my next allocation is going to come from, well, I'm in a good spot here because now I know exactly the exact heap layout and how things are going to work, so I can position my heap properly. So how does this work? So first, we're going to try to look in the cache. If it's an exact match, then we take the cache. Okay, great. Otherwise, you're going to look in the free list. Does the free list have an exact match? It does. Great. It doesn't. Okay. If it doesn't have it, we walk up the free list and we try to find one. So like I said before, if I try to allocate from 3, if I don't have one in 3, I'm going to walk to 4. If I try to allocate from 5, I don't have one, I'm going to try 6, and so on and so forth all the way down the line. And if you don't do any of that, lastly, we have to allocate from the region. We're going to grow the region out a bit. Here's a picture of the region. Like I can say, the general idea on how to do this is you just allocate blocks from the back of the region. I'm going to show you how to do that calculation in a second. But before we do any of this, any of the demos, I just have there's a disclaimer. This script is available on the GitHub as well, and what it does is it forces all allocations on the same core. If you're trying to debug with LDB, every time you hit a breakpoint, it blocks the kernel. So every time it blocks the kernel, it wakes up on a new core. So anytime I was trying to debug anything with LDB, every breakpoint I hit was a new core. So this was nearly impossible to actually do anything with. So we went ahead and wrote this stupid little script that just hooks all of the choices and forces them all to be 1. But another way you could do this is you could simply patch malloc out to always return 1, which is probably slightly faster because this is a little slow when you're running on big programs. Okay, and now here's the region idea. So we have this bitmap, this large bitmap that kind of is just a mess. But you can see there's a 0 there, two zeros, 4 zeros, so on and so forth. And if we continue on, you can see the free list looks like that, and they're actually represented there. So what this bitmap allows us to do is to get those heap overflow techniques and massage this heap in a perfect way. We can actually physically look at it and say, hey, look, I have these slots. How do I fill these slots? What can I do? And what can I overflow? So for instance here, if we wanted to fill these slots, you can check out how many slots there are. There's 56. You can believe me, it's 56. You can add up all the numbers on the free list. That adds up to 56. So there's 56 open slots. So what does that mean? That means we need to make 56 single quantum allocations, and that whole bitmap's going to be flat. Okay, so why do we want a flat bitmap? As Alex Sotorov said when he did heap function back in the day, you make a bunch of allocations together, well, then your next allocations are going to be together. They're going to be next to each other. So if I have an object I want to put here, I have a buffer I can overflow, well, now I have a place I can put them to be exactly next to each other. And so notice the length of the bitmap here is 901. I make a 24 quantum allocation, the same bitmap, it's now 925. So that's generally how you would grow the bitmap. And all those allocations are going to come off the back end, and they're all going to be right next to each other. Okay, double frees aren't possible, they're checked against. So on 64-bit OS X and iOS, heap spraying is not entirely possible. It is possible, and it's totally a doable technique, but it's not possible to get a real reliable, elegant exploit out of heap spraying. It's not like it used to be a couple years ago. There's a lot of structures and things in your way. They actually place these heap structures in strategic points, so that way, if you're just doing heap spray, you're actually going to run into some of these problems. You're going to run into some of these heap structures. You're going to overflow things that are important. So heap spraying is not super useful on OS X nowadays. Okay, I'm going to talk 2 seconds about LDB, and then I'll do a demo, and then we'll talk about the exploit, and then we'll be done. So has anybody here used LDB? Show of hands. LDB, anybody? Anybody? Does anybody like LDB? Can I get a hand for anybody that likes LDB? No. That guy over there, okay, good. Some people like LDB. It's okay. It's a good debugger. It does what it does. But so some of the problems with LDB are things like this. I want to set a breakpoint on main. I want to set a breakpoint address of main. So I have to use C-type casts to cast my thing to main, or I can, and if I want to add a breakpoint command, you can only add one breakpoint command. I can't say print out RIX and continue. I can only do one. So things like that were extremely inhibiting and cumbersome to deal with. And the Python functionality inside LDB is humongous. It has thousands and thousands and thousands of functions. So we said, what can we do about this to fix this? So I think most vulnerability researchers are going to say WinDebug is the ultimate debugging framework. It's the best debugger. So what we do is we took all the commands we liked out of WinDebug, and we put them in LDB. Not only did we do that, we also made an extremely generic way of adding functions. We put a template. You just add the template and write your function, and it's wham, bam, thank you, man. Very, very, very easy. Whereas the traditional LDB way is probably 30 or 40 lines to write a basic hello world LDB function is like 30 or 40 lines. Well, our hello world function is 1. So it just makes it a lot easier. That being said, we will go through a demo. I'm going to show you guys, we're going to predict some allocations here. Let's clear this out. Can people see that? Or do you want bigger? Bigger? Okay. That better or still bigger? 48? That's good, right? Sweet. All right, it's going to be hard for me to work. That's okay. Okay. All right. So first things first, I just want to show you guys the code. All we're going to do is we're going to malloc 10 blocks. We're going to free 10 blocks. This is just to pull some information out from the region to fill up our free list so we have some data to work with. We're then going to malloc 9 quantum. 9 quantum because if you go through a 10 loop, the last item is 9. So that means the cache is going to have a block of 9. So we're going to grab that off the cache to prove that we can do that. We're then going to grab another 9 quantum allocation from the free list. So we can prove we can do that. Then we're going to clear the free list, and we're going to allocate from the region, just to show you guys how that works and to give you an idea of what we're doing. Okay. So we started up. That's so bad to see. All right, so I load up my little Heap script. I know it's really hard to see. But, so A is our overarching zone structure. I know it's impossible to see, but this is all on the GitHub as well. You can check it out. You can even follow along. That's the overarching magazine. And so I told you I forced everything in the first magazine, so I already set that up. So T is magazine 1. T is magazine 1. We have our bitmap here. I know it's really hard to see, I'm sorry. There's a bitmap there. Here's the free list. And then what we're looking for is actually this mag last free right here. And what this is representing the cache. Mag last free, M size 9, 9 quantum, 9 times 6 is 144. That's the next thing we're going to allocate. So just remember this number, 102, D00. That's where our cache allocation is going to come from. Let's continue on. Continue on. Malloc off the cache at 102, D00. Okay? Now simple stuff for malloc. Notice we're going to allocate another 9 quantum allocation. So we'll reload up all our stuff. And then here we can do print t.dump. Pre.dump is all it's going to do is dump the free list out for us. And then hopefully by now you guys can generally understand that we're doing a 9 quantum allocation off of the free list. What's it going to do? It's going to go to the first size it possibly can. So what's going to happen is we're actually going to get an allocation from 1001 3510. So if we close it out, continue on, notice that's where the allocation comes from. So at this point we've now predicted both of those extremely accurately. So now we're going to continue on, clear the free list out, and we're getting ready to make a 10 quantum allocation. So how is this going to work? This is slightly different, right? So just to make sure that everything I said was correct, we do print t.dump. There's nothing there. So what we're going to do is you look at T. You can't really see it here, but there's number of bytes of magazine. There's number of bytes free at end. All those things I was showing you before, that picture showing the available bytes. I'll show you how to calculate all that out. If you do T first node, which is just accessing the region, .t, what that's going to do is that's going to give us the base address for the region. And then from there, we can take that base address and do a little math with it. So you take the number of the bytes in the magazine, oops, and you subtract it from the number of bytes free at the end, plus the base of the region. Oops. And so we do this out. I'm assuming I'm confusing everybody and nobody's understanding this, but that's okay. All right, that's not the right number. 0x, 1, 0, 0, 1, 1, 2, 3, 4, 5. Okay, so now we do that out. We get a number, 3BA0, and I know it's magic and whatever, but notice it is 3BA0 that actually gets allocated off. So that is indeed how that works. So before we move on from this, I just want to show you guys a couple things. Okay, so this is your standard, this looks like shit, but this is your standard LDB output, nothing to it. It doesn't give you registers, doesn't give you anything you want to see. So if you wanted to see registers, you can do register read, and that's how it prints out registers for you. So if you want to know what the registers are, that's how you do it. Okay, so now I want to know disassembly. Like you can just tell this is very cumbersome. So we wrote this LDB in it. So there's something called H. H shows us all the registers. H gives us a nice hex dump output, and H gives us a nice disassembly. Notice about disassembly is that it actually disassembles backwards. There's no LDB in it or script that can actually disassemble backwards like this. So if we wanted to see even further backwards, you can do like backwards 20. And now it gives you 20 backwards. And so as reverse engineers, you know that a lot of times it's not where you're going, it's where you came from. So the fact that LDB doesn't have anything to show you all that good stuff is a little bit frustrating. Okay, now let's say we wanted to know where this type H. Let's say we wanted to see what's at this pointer right here, or this pointer right here. Let's do this one. So then we would do regularly you would do something like x/4x money sign RSP plus 24, and that's gonna get you this number, and you get a couple outputs. But what we can do is we can do stuff like DW, and then you can do POI. Same thing as WinDebug, and what POI is going to do is actually going to dereference that address and give you real output. And so notice it's giving you in Word format all the data, and it also gives you the textual output here on the right with a nice text dump format. Okay, so that's a super helpful way to dump data. Another interesting thing here is what happens if you wanted to find an image. Let's say you wanted to reverse malloc, like I did. You type image list, and then you would search through this list. You'd look through it by hand, or you'd copy and paste it out and try to find the word malloc. That's the general idea here, right? It's in here somewhere. Malloc. Okay, I can't find it. I don't know where it is. So we wrote a thing. So you do lm malloc, and there you go, libsystem malloc. Okay, well let's say I want to know the malloc I'm using currently is on the malloc I want. I want to know what other potential mallocs can this program use. So you do ls list symbols malloc. And now it's going to give me a list of every malloc in this program, every dylib that is currently being used. It gives me all their mallocs. Again, something totally not possible with LDB. That's super useful. Again, as reverse engineers, a lot of times we just want to reverse calls, right? A lot of people call it call site reverse engineering, whatever. You simply reverse engineer from one call to the next call, right? You just want to follow the calls, because a lot of times you can get the idea of what this program's doing just by looking at what library functions it's calling. If you can see it's calling malloc 5 times and then it calls some network operations, you have a general idea what this program's doing without reverse engineering anything. Well, that's really hard to do in LDB. So if you do something, we wrote another function, and this just simply returns all the calls, or you can return all the jumps, or anything you want. I mean, every time the word RAX is used, every time that register is used, if you can do taint tracing, you can do all that kind of stuff just based off of this little dsearch. And then was there anything else I wanted to show you with this? We got about 8 minutes left, so I'm trying to think. Oh, the only other command I want to do is history. So what history does for us, let's just run it one more time. What history does for us is it's going to give us information about malloc blocks. So first it's going to tell me that it doesn't have stack logging enabled. You have to enable that. So we enable stack logging, we do it one more time. Okay, grab that block, and you type in history. So instead of having to go to another terminal and do all this stuff to get malloc stack logs off of something, I now have malloc stack logs, where all this stuff came from, right here in LDB. If I tried to use LDB's tool right now, it would crash this and it would ruin my demo. The last thing that LDB can't do is, so you're doing exploitation, right? You change your page permissions so you can run your shellcode, right? But when you change your page permissions, you should probably verify that your page permissions have changed, right? You don't want to try to execute non-executable code, because then you're going to crash. Okay, LDB, let me look at page permissions. Oh wait, I can't look at page permissions. Well, what kind of debugger can you not look at page permissions? That's absolutely terrible. So I have to now go to another terminal window, open my maps, search through my maps, and try to find the page permission of this. So what we did, we just wrote a thing called address, very similar to bang address, and you just put your address in there. You unfortunately have to be root, because you have to actually access the system's maps. But you put your address in there, and you let it do its little searching thing. Hopefully it doesn't take too long. And it should come back with some information about there you go, sweet. So now I have page permissions on that, read-writable, as expected, on the heap right there. That's another thing LDB can't do. I highly recommend anybody use LDB. Check out this init. I think it's the best init available. We have full breakpoint management, full expression parsers. Almost every WinDebug command you can think of is here. It's been a lifesaver since we started, and that's why I'm talking about it so much. All right, any questions about the demos or anything of that nature? Otherwise, I'm going to spend the last 5 minutes talking about the Safari exploit. And then I'll have 10 to 15 minutes for questions, and that's it. Sweet. All right, exploit strategies. Okay, so there's a lot of problems that have come into play here, and I think I've tried to hint at them a little bit. A major issue here is the fact that WebKit uses malloc. WebKit uses bmalloc. WebKit's malloc, right? So anytime WebKit calls malloc, it calls WTF malloc. It doesn't call system malloc. So I have a heap overflow in system malloc. Well, that's great, but I have no access to anything WebKit malloc. So that means that I have really no way to access any of my objects through JavaScript. I have no way to manipulate my heap through JavaScript. I have no way to do any of these sorts of things. But I mean, at a surface glance, there's no way to do any of that. So this is all default malloc zone, and everything that I need is in WebKit malloc. So how do I do these things? What do we need? We need an information leak, and we need an object. The great thing about the object overwrite is there's actually a core foundation object that gets allocated right after our buffer. That's very easy to overwrite and very easy to get RIP control. We just lucked out with that. So with this bug, when I first fuzzed it, I already had RIP pointing to 41414 right off the bat because of the object we're overwriting. It turned out really, really easy. But what the problem was the information leak and actually getting all this into WebKit. So almost every allocation you control from JavaScript goes into WebKit. But on OS X, the calls to new, not all calls to new, but a good portion of the calls to new are going to go into our default zone. So this is going to open up objects for us to overwrite, and this is going to open up a way for us to start to massage our heap a little bit. At this point, we still need an information leak. So we found some heap massaging primitives via audio context. With audio context, you can allocate 3, 4, 5 quantum allocations, and you can actually position your heap pretty effectively. At this point, we also need multiple images to position our heap. So now we're using CSS, a custom server, to load up multiple TIFF images, get information back, rewrite brand new TIFF images using libtiff and a couple other techniques, rewrite new TIFF images to actually try to exploit this thing. So now you're communicating to the server multiple times. Obviously, you can tell it's getting kind of cumbersome. It's getting kind of big, but it still works. So that's a positive. Okay. So then we reversed and reversed and reversed. We reversed for weeks. We came up with a couple of techniques. We scanned the entire heap base for pointers. Any pointer we can find in the heap, in default heap that is, where are these pointers going to? What pointers can we control? Because we're trying to find any object, any allocation that's potentially on our heap that we can access through JavaScript. We're trying to find anything. The only thing we find is date.prototype.toLocale, and it literally has like a millisecond where you can overwrite it. So what happens is they allocate date.prototype to locale. It sits there for a couple seconds, and then it gets copied over into JavaScript space. So it comes from default user space into JavaScript space. In that tiny, tiny window, we have to overwrite the null byte, so that way when JavaScript tries to read this back, we have our information leak. This is extremely unreliable, this is extremely difficult, this is extremely hard to find, but it works. So it's 3 quantum allocation, and we do our metadata overwrite to do a backwards coalesce to get our use after free happening. Then we put ourselves in the middle locale string with some heap positioning, some of the JavaScript the heap massaging techniques using audio context we talked about earlier. And then we can remove the null terminator, read the date back, and get some information out of it. Once we have the information leak, you call that back to the server. The server rewrites a brand new TIFF, now knowing its base address. Like I said, object overwriting was very, very simple. And then we had code execution after that. Another thing I failed to mention about how difficult this was is the fact that if you overwrite a free list, if you overwrite any free block, there's checks to ensure those free blocks are not modified. So as soon as you modify a free block, your exploit then fails. So the other thing we had to do is we also had to massage the heap in such a way that we clear all free blocks out. So when we clear the region, like I showed you, and make sure all allocations are coming from the back end. If allocations come from anywhere in the middle, there's a 9 times out of 10 chance you're going to hit a free block. You hit that free block, overwrite in the free block, and your exploit fails. So yeah, and there's the tool. There's the LDB in it. There's my Twitter account, and yeah, that's it. I'm sorry if it's a little hard to understand, but I will be around this afternoon today and to talk about it if anybody's interested in chatting. I will be more than willing to talk about more about it. I would show you the exploit, but I don't think you guys want to see me run Safari 100 times to get one exploit. It's not reliable, it's not great, but it was a lot of research, a lot of hard work that went into it, so I think that is better than the result. But all right, that's all I got.
Awesome. Did you guys follow that? Dude, you're a fast speaker.
Sorry about that, yeah. I'm a little nervous.
Yeah, it's all right. It's all right. We recorded it, so we can go back and rewatch it, maybe slow motion. No, but it's awesome. It's a lot of research behind this. It's a lot of work you guys do.
For sure.
Yeah. Well, the tool's online. There's tools online to play with. So you good on time. Do we have questions from the audience for this? No. Do we have a microphone for that? No, we don't. Oh, there should be one over here. No, it's not. I have no microphone.
It's all good. You just tell me a question, I'll repeat it.
You mentioned cookie protection.
Mm-hmm.
It's very similar to the tripwire controls I've seen in Windows 10 when it comes to like out-of-stack memory migration.
Mm-hmm.
Have you seen any other tripwires like that in OS X that seem like?
No, not so he's asking if there's any other type of like cookies or hang-ups, if you will, in the exploitation side of things. And no, the biggest hang-up is that thread migration issue. And what I think they had is that they came up with this new idea, this better Heap implementation, this better malloc implementation. And it doesn't, with this migrating threads, it makes it so difficult to exploit that I don't think they actually need any of those checks anymore. Like they're kind of at the point now where their Heap implementation is so advanced that's not the most important thing for them. But yeah, they have two separate checksums, two different kinds of checksum algorithms that are small hang-ups, but other than that, no. But even the checksum implementation themselves, they're almost deterministic. Like not totally deterministic, but they're about like 30 to 40% deterministic. So you can actually, if you do enough analysis, you can actually come out with a more strategic way of doing it. So it's not totally random.
Now we have a microphone. So more questions? Yes, one in the background.
You were saying that heap overflow were almost obsolete by now. Why do you see that?
Oh, just because it's no fact that, Heap overflow is not obsolete, but Heap overflow in the default malloc on OS X is pretty much obsolete. The reason I say that is because of that thread migration issue, it's so difficult. And Heap overflows are just, they're a very, very difficult beast. So if I had Heap overflow in WebKit, for instance, I think that's definitely exploitable. But the amount of research and work that goes into Heap overflow versus another class of bug like a use after free is astronomical. Like you're going to spend a couple weeks, couple months on a Heap overflow, whereas a use after free bug might take a week or two. So they're much more difficult. They're much, like I said, like he was talking about, there's a lot of tripwires, there's a lot of checks on Heap overflows. It's very easy to detect whether you have Heap overflow. It takes a lot of control to exploit Heap overflow. Use after free is just infinitely simpler. So while I say it's obsolete, I don't mean that. I mean it's totally possible. It's just a much more advanced technique. It's a much more advanced exploit.
More questions?
Again, like I said, I'll be around. I know it's intimidating to ask questions in front of people, but I will be around eating lunch and stuff and hanging out, go to the bar, whatever. So feel free to come up and talk if you're interested.
All right, no more questions in that case. Thank you very much, Tyler.